Okay, so starting on exam 2, we're going to do some integrals, and by some I mean a ton, and then we're going to do just a little bit of sequence stuff. So let's go ahead and get started with number 1. So here are all our expressions. Let's go ahead and work on those. So the first one is integral of t e to the 0.3 e to the 0.3 t dt. So okay, I have t times e to the 0.3 t, so it doesn't look like I can do a u sub. I don't see any square roots, so it shouldn't be a trig sub. No fractions, so it shouldn't be partial fractions, so then my only real option is integration by parts. Again, I see a t, I see a times e, so I'm thinking integration by parts. Then I consult the isolate table, and that'll give me u, du, v, and dv. So what should I pick for u? That should be t. What should I pick for d? No, you don't pick du. du is the derivative of t. So you would get 1 dt. That forces dv to be e to the 0.3 t. So then if I integrate e to the 0.3 t, because that's how you get v, v is the antiderivative of dv, I'm going to get 1 over 0.3 e to the 0.3 t. So the 0.3 is the same thing as 3/10. So in other words, this is 10/3 e to the 0.3 t. Okay. So now, by integration by parts, this is uv. So this is going to be 10/3 t e to the 0.3 t minus integral v du, except I can pull out this 10/3 because it's a constant. So 10/3 v du just gives me e to the 0.3 t dt. So this is technically a u sub. Technically a u sub. And that's how I got v in the first place, was a u sub like that, where u is equal to 0.3. And that's how you get the 10/3. We're going to do that again. This becomes 10/3 t e to the 0.3 t minus 10/3, another 10/3 e to the 0.3 t. And then it's an indefinite integral, so I slap on that constant of integration. And so we end up with 10/3 t e to the 0.3 t minus 10/3 squared e to the 0.3 t plus c. And maybe let's go ahead and factor just for the practice, although that top line would be fine. This would be 10/3 e to the 0.3 times t minus 10/3 plus c. So why would I do that? Because I might be interested in zeros. Maybe I can figure out what the c is. That would be helpful for that. But either way. So then that was part A. So let's take a peek at part B. We're going to integrate integral of arc sine of x, which just for notation's sake, because I could write it either way, is the same thing as sine inverse. So how do I integrate this? So at first this seems kind of spooky, but it's really not that bad, because what I can do is I can say, okay, the trick is you let u be equal to 1, in which case, oh, sorry, not u. You let u be arc sine by isolate. U is arc sine. So du is this 1 over the square root 1 minus x squared, because that's the derivative of arc sine. And then the trick is you say dv is actually 1. There's a 1 there in front of that arc sine because I can multiply something by 1 without changing it. And so that makes v equal to x. So by that, this integral is equal to uv. So x arc sine x minus integral v du is x over the square root of 1 minus x squared dx. Now we let u be equal to 1 minus x squared. Du would therefore be negative 2x dx. Or writing it the other way, dx is du, let me write an x over minus 2, because I have an x dx here. And now I'm going to rewrite this. This becomes x arc sine of x minus integral. I have x dx, but now this has to be a minus 1/2 du, because I have du over minus 2, divided by 1 minus x squared was u, so divided by the square root of u. So this is x arc sine x. The minuses come together to make a plus, 1/2 integral du over root u. And again, you can do this in less steps if you want, but just so I'm showing everything. This is x arc sine of x plus 1/2 integral u to the minus 1/2 du. And now it's ready to do power rule on. So this becomes x arc sine of x plus 1/2 integral, or not integral anymore. By power rule, this becomes u to the minus 1/2 plus 1, or 1/2. And then my trick for working these problems is if you have a fraction, you put the thing here that would give you 1 if you multiplied the exponent. And the reason for that is you would essentially want it to cancel when you took a derivative, right? Here, you pull the constant out of the integral, so there's always a 1 in front. So you take your new power, that's the thing plus 1, take a reciprocal, and that gives you this number. You can use the formula for the power rule. It gives you the same thing. I just think this is more intuitive and helps you get at it a little quicker. But now I have 1/2 times 2, so that's just 1. And u is equal to 1 minus x squared. So this is x arc sine x plus the square root of 1 minus x squared plus c. Never forget the plus c. And so that's all we can do there. This is A, by the way. A. And now finally we do part C. So this one has a star on it, which means it's a little more challenging, but still good practice. So integral from square root pi over 2 to square root pi theta cubed, nope, not secant, just cosine. Cosine theta squared d theta. And at first you might be worried and you say, uh-oh, there's not a u substitution, like, do I want to do integration by parts here? Because there's a theta cubed and a cosine of theta squared. And both of those just seem like they would be really awful integrals to have to do. So there's a trick here. And that is, you rewrite this as the integral of square root pi over 2 to root pi of theta cubed. Oop, I missed the trick. theta squared times theta times cosine theta squared d theta. So again, not maybe immediately obvious why we would do this, but there's a good reason. I can now let u be equal to theta squared. Du would then be 2 theta d theta. And now, aha! This is a theta squared, and this is a theta squared. So this now becomes integral. Also, let's go ahead and change those bounds while we're at it. U of square root pi is square root pi squared, or just pi. U of the root of pi over 2 is pi over 2. So now this is the integral from pi to pi over 2. And then what happens? This theta squared is equal to u. So is this one. So I get 1/2, because du is equal to 2 theta d theta. I have 1 theta d theta. So then I lose a 1/2, or I have to divide by 1/2. And then this becomes u times cosine of u du. And now this is a very reasonable integral that I could give you. And sleep very soundly at night. So integral from pi to pi over 2 u cosine u. Now we do a integration by parts again. I've already got u, so let me call it v and w. That's perfectly fine, especially since I don't even keep these names. So by isolate, v should be u, which would make dv 1. dw would be cosine of u, which would make w sine of u. This is a u, by the way. And so I get this is 1/2 vw, which is u sine u, minus the integral of v du, or w dv, which is integral sine of u du. And I'm going to write this here, evaluated from pi over 2 to pi, because I have seemed to run out of room. Okay. And so now, I don't want blue anymore. This is 1/2 u sine u, evaluated between these 2 points, minus the integral of sine is negative cosine, minus cosine, because if I take a derivative of cosine, I would get minus sine. Again, evaluated from pi over 2 to pi. So now we plug in. This is 1/2. Let me do this at least a little bit easier. Put everything together so I can plug everything in at once. Minus, or minus minus gives me a plus. And this x should be a u. Evaluate that from pi over 2 to pi. And so I get 1/2 pi sine of pi plus cosine pi minus 1/2 pi over 2 sine of pi over 2 plus cosine of pi over 2. Put this together. Sine of pi over 2, or sine of pi is 0, so that goes away. Cosine of pi over 2 is also 0, so that goes away. And I'm left with cosine of pi is minus 1. Sine of pi over 2 is 1. So I get minus pi over 4. And now let's think a second. Does that make sense? Yeah, because we had pi over 2 to pi of u cosine of u. So from pi over 2 to pi, cosine is negative, but u is positive. So that means this function is negative that whole time. So it makes sense that we get a negative answer. And that is our final answer. And that is how you do those 3 integration by parts problems.